Welcome back to this channel for practice problems for actuarial exams. My name is Krzysztof Ostaszewski. You can find information about me at smartyurl.it/Jedi. My advice on how to pass actuarial exams is at smartyurl.it/pass. This video channel is at smartyurl.it/pass actuarial exams. Here you have information about online seminars for exams PFM, IFM, and LTAM, as well as the study manuals for those that I offer. I direct the Actuarial program at Illinois State University. You can find information about it at smartyurl.it/actuary. If you would like to offer a tax-deductible donation to support our students, please go to smartyurl.it/help-ISU-actuary. Here's the problem for today for exam LTAM, Long-Term Actuarial Models. Written answer section problem number 1 from the last exam. Tim, age 50, purchases a semi-continuous whole life insurance policy with a death benefit of $100,000 payable at the moment of death. Premiums are payable annually. You are given that initial expenses are $500, maintenance expenses payable at the start of each year, including the first, are $50 per year plus 5% of the gross premium. Mortality follows the standard ultimate life table, which you can find at smartyurl.it/SULT. Deaths are uniformly distributed between integer ages. Interest rate is 5%. Part A. Question A. Show that the gross annual premium calculated using the equivalence principle is 1280 to the nearest 10. You should calculate the value to the nearest 0.1. Part B. Show that SQ 80.7 is 0.033422S for S between 0 and 0.3. Hence, write down an integral expression for A bar 80.7 colon angle S with a 1 above the 80.7 indicating term life insurance for S between 0 and 0.3. Show that 100,000 A bar 80.7 colon angle 0.3 with a 1 above 80.7 indicating term life insurance is 995 to the nearest 1. You should calculate the value to the nearest 0.01. Question C. Show that the gross premium reserve at time 30.7 for this policy is 52,620 to the nearest 10. You should calculate the value to the nearest 0.1. D. Explain why applying linear interpolation to the gross premium reserves at time 30 and time 31 would not give a good estimate of the gross premium reserve at time 30.7 in this case. Part A. So let's write capital G for the gross premium, which is a standard notation. Using the equivalence principle, we write that actuarial present value of premiums, so G A double dot 50, is 100,000 A bar 50, that's the cost of life insurance, plus 500, the setup expense, plus 50 A double dot 50, which is the recurring annual expense, plus 5% annual premium recurring expense, so 0.05 recurring in first year, every year 5% of premium, so 0.05 GA double dot 50. We also have, and note that I over delta is 1.02480 from the last page of the table, where you take I over I upper M for M going to infinity. So A bar 50 under uniform distribution of deaths is equal to I over delta times A 50. And from the table, that's 1.0248 times 0.18931. So it's approximately 0.19400,489. And A double dot 50 from the table is 17.0245. So we solve this equation for G. G is equal to 100,000 A bar 50 plus 500 plus 50 A double dot 50 divided by 0.95 A double dot 50. Plug in all the values that we just established, and we get approximately 1,283.08668 for the gross premium. For this part B, we begin by noting that 0.7 plus SQ80, probability of dying, 80-year-old dying within the next 0.7 plus s years, but that's a fraction of the year because s is less than 0.3. That's equal to 0.7 Q80, probability of dying in the first 0.7 of the year, fraction of the year, plus given survival through the 0.7 of the year, probability of dying in the remaining part of the year, which is SQ 80.7. Since deaths are uniformly distributed between integer ages, we have 0.7 plus SQ80 is equal to 0.7 plus S times Q80, and 0.780 is equal to 0.7 Q80, and 0.7 P80 is equal to 1 minus 0.7 Q80. So we conclude that 0.7 plus SQ80 plus is equal to 0.7 Q80 plus 1 minus 0.7 Q80 times SQ80.7. Well, we're looking for this SQ80.7, so we solve for it, and SQ80.7 is equal to 0.7 plus S times Q80 minus 0.7 Q80 over 1 minus 0.7 Q80. And then, of course, 0.7 Q80 minus 0.7 Q80 is 0, so in the numerator we only have SQ80 and the bottom is 1 minus 0.7 Q80. And Q80 can be looked up in the table, and it's 0.032658, so we plug it in and do the calculation, and this comes out to be approximately 0.033422205S, and that's what we were asked to find. Note that the derivative of this expression with respect to S is the constant under uniform distribution of deaths, probability density function of the future lifespan of 80.7 for S between 0 and 0.3. And the derivative is that constant that you see there, 0.033422205. For the second part, we have A bar 80.7 colon angle S with 1 above the 80.7 equal to the integral from 0 to S of 1.05 to a minus t, that's a discount factor, times TP 80.7 times mu 80.7 plus t, and this is the PDF of the lifespan of the person between ages 80.7 and 81, and it's constant because of the uniform distribution of deaths, and it's equal to 0.033422205. So we put out that constant. In front of the integral, we have the integral from 0 to S of 1.05 to minus t dt. That integral, of course, is A bar angle S under delta, the force of interest, equal to the natural logarithm of 1.05. And therefore, 100,000 A bar 80.7 colon angle 0.3 with 1 above the 80.7 is equal to 100,000 times 0.033422205 times A bar angle 0.3 at delta equal to 1, a natural logarithm of 1.05. And we just calculate then, this is 3342.20481 times 1 minus 1.05 to a negative 0.3 over the natural logarithm of 1.05, that's delta, and that's approximately equal to 995.359112. Let's for part C, let's denote the gross premium reserve at time t for this policy by TV. So we have this recursive relationship that 30.7V is equal to 100,000 A bar 80.7 colon angle 0.3 with a 1 above 80.7 plus 0.3E 80.7 times 31V. And 31V is 100,000 A bar 81 plus 50 A double dot 81, that's the expenses, minus 0.95, that's premium available after expenses, 0.95G, A double dot 81. Under uniform distribution of deaths, we write this as 100,000 times I over delta A 81 plus 50 minus 0.95G times A double dot 81. And using the data from the table, we just plug in everything, and also the value of the premium we found at the very beginning. This is approximately 52,918.87. Then 0.3E 80.7 is equal to 1.05 to negative 0.3 times 0.3 P 80.7 And using both uniform distribution of test assumption and standard ultimate life table, we write this as 1.03 to the negative 0.3 times 1 minus 0.3 times 0.033422. That's simply 0.3 P 80.7 written as 1 minus 0.3 Q 80.7, and that's 1 minus 0.3 times Q 80.7. And that's approximately 0.97558864. And therefore, 30.7 V is equal to 9953.359112 plus 0.97558864 times 52,918.87. That's approximately 52,622.41. And interpolating between these reserves at times 30 and 31 would ignore the fact that the reserve will increase immediately after the premium is paid at time 30. Instead, interpolating between the sum of the reserve at time 30 and the premium paid at 30, which would be the initial reserve for the next policy year, net of expenses, of course, and the value of the reserve at time 31 would give a reasonable estimate of the reserve at time 30.7. Please remember this is copyrighted material. The problem itself belongs to the Society of Actuaries. The solution is mine. Good luck in your studies and good luck on the test.